Welcome back. In our last video, we completely shattered the illusion of high school trigonometry. We looked inside your pocket calculator and discovered a shocking logistical truth. A microchip doesn't own a ruler, meaning it can't draw physical triangles in the silicon to find the answer. We also learned that it completely skips heavy algebraic formulas like the Taylor series. Why? Because early digital processors were incredibly weak. Forcing them to do massive complex multiplications and divisions would completely drain the battery, overheat the tiny processor, or just flat out fail because division and multiplication were simply too expensive for the hardware to handle. Instead, we discovered the machine uses the CORDIC algorithm to play a brilliant game of hot and cold. By relying on a hard-coded cheat sheet of magic angles, it zigs and zags its way right to the target. We broke down the math behind rotating a vector by updating its x and y coordinates, and saw how choosing those specific magic angles allowed us to replace heavy multiplication with instantaneous binary bit shifts. At the end of that movie, I left you with a puzzle. Take those pieces and write out the CORDIC loop yourself. I'm sure a lot of you completely nailed it, but whether you successfully cracked the code or are just here for the reveal, let's take a look at the raw engine. Here's the exact algorithm in action, right before we tackle that pesky stretching factor. This is our starting point on the graph. We create a vector of length 1, lying completely flat on the horizontal axis. Its x-coordinate is 1, its y-coordinate is 0, and because it is flat, its starting angle is exactly 0 degrees. This tells the computer to repeat the following block of code over and over again, counting up by 1 each time until it hits our maximum number of steps. Each loop brings the vector closer to the target angle. This right here is the absolute crown jewel of the algorithm. Instead of forcing the computer to do expensive decimal multiplication using a tangent value, we simply divide our current coordinates by powers of 2. Why? Because in the binary language of a computer, this isn't actually a math operation at all. Just like sliding the decimal point to the left in base 10 instantly divides a number by 10, sliding the binary decimal point to the right. A hardware trick called bit shifting instantly divides the number by 2. Because each single shift cuts the number exactly in half, shifting it multiple times gives us exponential division. If we tell the computer to shift the bits to the right by our current step count, we are literally dividing our coordinates by 2 to the power of that step. It gives us perfect fractions, dividing by 1, then 2, then 4, then 8, and so on. Best of all, it is completely instantaneous and requires almost zero processing power from the microchip. The computer accesses its tiny, hard-coded memory chip, the lookup table, and pulls out the specific magic angle assigned to this exact step, e.g. 45.0 for step 0, 26.57 for step 1, etc. The computer accesses its tiny, hard-coded memory chip, the lookup table, and pulls out the specific magic angle assigned to this exact step, e.g. 45.0 for step 0, 26.57 for step 1, etc. If the answer is yes, we must rotate counterclockwise. To do this without cosines or sines, we cross the coordinates. We subtract the shifted y from x and add the shifted x to y. Finally, we add the magic angle to our running total to track our new position. If our current angle is higher than the target, we've overshot. We must rotate clockwise. We do the exact same crossover math, but flip the plus and minus signs. We then subtract the magic angle from our running total. The step is over. We take our freshly calculated x and y coordinates and overwrite the old ones, locking them in as the starting point for the next loop. Once all the iterations are finished, the loop ends. Because the sine of an angle on a unit circle is strictly defined by its vertical height, the computer simply spits out the final y coordinate as the answer. Let's pop the hood and look at the exact math happening in the processor. We are going to track the coordinates, the bit shifts, and watch exactly how this vector terrifyingly stretches out of control by keeping a very close eye on our y value. We want to hunt down a target of exactly 41 degrees. Before the loop even begins, we lock in our starting position on the graph. Our current x is exactly 1, our y is exactly 0, and our starting angle is 0 degrees. Step 0. A bit shift of 0 means we divide by 1, so our shifted x and shifted y stay exactly the same, 1 and 0. The computer asks, is 0 smaller than 41? Yes. So it decides to rotate up by our first magic angle, 45 degrees. We cross the coordinates. Next, x becomes 1 minus 0, which is 1. Next, y becomes 0 plus 1, which is 1. Our y value is now exactly 1. We add the magic angle, and our new position is 45 degrees. Step 1. We pull our new coordinates from step 0. Shifting the bits by one space means we perfectly divide them by 2. Shifted x is 0.5, and shifted y is 0.5. The computer checks. 45 degrees is bigger than 41, meaning we overshot. The machine rotates down by the second magic angle, 26.57 degrees. We cross the coordinates again, but flip the signs. Next, x becomes 1 plus 0.5, which is 1.5. Next, y becomes 1 minus 0.5. Our y value drops to 0.5. Our new angle drops to 18.43 degrees. Step 2. A bit shift of 2 means we divide our previous coordinates by 4. Shifted x drops to 0.375, and shifted y is 0.125. 18 degrees is smaller than 41, so we rotate up by 14.04 degrees. Crossing the math again, our next x drops slightly to 1.375, and next y climbs by adding that shifted x. Our y value climbs back up to 0.875. Our angle is now 32.47 degrees. Step 3. We shift by 3 spaces, dividing by 8. 32 degrees is still too low, so we rotate up by 7.13 degrees. Our next x becomes 1.26, and our next y pushes up again. Our y value breaks the barrier and hits 1.04. The angle hits 39.6 degrees. We are getting incredibly close. Step 4. We divide by 16 using a 4-space bit shift. 39.6 is still under 41. Rotate up by 3.58 degrees. Our next x is 1.2, and our next y keeps climbing. Our y value is now 1.12. Our new angle is 43.18 degrees. We slightly overshot again. Step 5. Divide by 32. 43 is too high, so we rotate down by 1.79 degrees. We cross the coordinates, subtract the angle, and our y value dips slightly to 1.08. We land at 41.39 degrees. Step 6. Divide by 64. We are just a tiny hair over the target, so we rotate down by 0.9 degrees. The math locks in our new x and y, and our y value nudges down to 1.07. The angle settles at 40.49 degrees. Step 7. Divide by 128. 40.49 is just under the target, so we gently nudge up by 0.45 degrees. The cycle ends, bumping our final y value to roughly 1.08. We land at a beautiful 40.94 degrees. With every single tick of the processor, the swings get smaller, and the vector h1's incredibly close to our target. But if you were listening closely to our y values, you can completely see the trap we warned you about. We started with an x of 1 and a y of 0. The sine of 41 degrees is supposed to be roughly 0.65. But by step 4, our x had bloated up to 1.2, and our y value completely blew past the right answer, hitting 1.12 and finishing at 1.08. The vector is stretching wildly out of control, flying completely off the edge of the true unit circle. So, how do we fix this? How do we shrink this mutated vector back down so it perfectly traces the edge of a unit circle with a length of exactly 1? As we saw in the previous video, this stretching isn't random, because we deleted the massive battery-draining multiplications from the original equations. Our algorithm strictly rotates the vector using bit shifts, but mathematically, performing this raw rotation without its matching cosine actually enlarges the vector by 1 over the cosine of the magic angle on every single step. Think about what that means. Step 0 stretches the line. Step 1 stretches it a little more. Step 2 stretches it again. We are multiplying the length of the vector by a chain of specific fractions over and over. But here's where the mathematicians save the day. Because our cheat sheet of magic angles is permanently fixed, the amount of stretching is entirely predictable. If you multiply all of those tiny stretching factors together infinitely, they don't grow forever. They actually hit a mathematical brick wall. The absolute maximum stretch limit of this algorithm is exactly 1.64676. If we look back at our hunt for 41 degrees, our final bloated y value was roughly 1.8. If we simply take that number and mathematically divide it by our stretch limit of 1.64676, We get 0.6558. Pull out your modern smartphone right now and type in the sign of 41. The answer is 0.6560. We completely nailed it. We completely nailed it. So, problem solved, right? At the very end of the loop, we just tell the computer to divide the final answer by 1.64676. Wait, stop. Do we really want to do a massive decimal division here? Absolutely not. The entire point of inventing this algorithm was to avoid expensive multiplication and division. Forcing the calculator to crunch a massive decimal division at the very end of the program completely defeats the purpose. It would lag the processor and drain the battery. So, the engineers did something brilliant. They pulled a mathematical time travel trick. Instead of dividing the answer at the very end of the algorithm, they divided the starting point at the very beginning. Remember our standard start? We always start completely flat on the graph, with a y of 0 and an x of 1. If we divide our starting y of 0 by 1.64676, it remains 0. But if we divide our starting x of 1 by 1.64676, we get a highly specific pre-shrunk decimal, 0.60725. The engineers took this pre-shrunk number and permanently hard-coded it into the microchip. This is the magic seed. By forcing the computer to start its journey at an x of 0.60725 instead of 1, the outward spiral still happens. The vector still mathematically stretches and grows wildly with every single zigzag. But because we artificially shrank it at the starting line, the timing is absolute perfection. On the final step of the loop, stretching vector seamlessly expands until it exactly kisses the edge of the true unit circle, instantly delivering the flawless sine and cosine, all without doing a single heavy division. Now that we have finished developing the CORDIC algorithm, let's compare it to the Taylor algorithm. Our mission is simple. Find the sine of 41 degrees, pushing both algorithms until they reach an error margin of just 0.001. But in the brutal world of microchip design, not all computer operations are created equal. A simple addition costs almost nothing, but a heavy multiplication or division burns through battery life and processing time. So let's weight our actions like a hardware penalty scoreboard. Additions and subtractions cost 1 penalty point. Bit shifts cost 1 point. Heavy multiplications cost 40 points. Massive divisions cost 50 points. Let's look at the Taylor series first. To calculate the sine of 41 degrees, Taylor must first convert degrees into radians, requiring an initial setup tax of 40 points for a heavy multiplication to establish our squared variable. Then, it unleashes its infinite expansion series. To reach our target accuracy, Taylor has to crunch 4 full terms. For each loop, it performs 3 heavy multiplications to update the numerator powers and the denominator factorials, plus a massive division to compute the final fraction, along with 3 additions and subtractions to move the sequence forward. When we tally up that hardware tax, every single step through the Taylor loop costs a staggering 173 penalty points. Across 4 terms, combined with our setup tax, Taylor finishes its run with a massive total score of 732 penalty points. It gets the right answer, but the processor sweats heavily doing it. Now let's look at our fully developed CORDIC algorithm. Instead of heavy algebra, CORDIC starts with our pre-shrunk magic seed and plays a game of hot and cold, zigzagging toward 41 degrees using its hard-coded cheat sheet of magical angles. To achieve that exact same precision, CORDIC takes 10 steps down its lookup table. Let's tally up the CORDIC actions: 0 multiplications, 0 divisions. Instead, at every single step, it uses 2 instant binary bit shifts to simulate division, and 3 simple additions or subtractions to update the coordinates and track the angle. Because shifts and adds only cost 1 point each, the total cost for a single CORDIC iteration is an incredibly cheap 5 penalty points. Across 10 full steps, CORDIC finishes its entire run with a total score of just 50 penalty points, 732 points versus 50 points. That is exactly why your calculator doesn't use classroom whiteboard algebra. By cleverly outsmarting the hardware and trading heavy algebraic multiplication for free bit shifts, CORDIC wins the heavyweight title, saving your battery and delivering the perfect answer in a fraction of a second. To truly understand why CORDIC is the undisputed champion of your calculator, we ran a simulation. We mapped out the exact hardware penalty costs for both algorithms to find the sine of every single angle from 1 degree all the way to 90 degrees. Let's look at the Taylor series first. Look at this red line. It looks like a terrifying set of stairs. This is the fatal flaw of the Taylor series. As the angle grows larger, the starting value of x grows larger. And because it's an infinite series, the algorithm has to chew through more and more loops just to safely shrink its error below our target precision. Every time Taylor is forced to calculate another term, it is slammed with that brutal 173-point penalty. By the time it approaches 90 degrees, the processor is chewing through power and the graph steps higher and higher. Now, let's look at CORDIC. It is a perfect flat line. CORDIC does not care if you ask it for the sine of 1 degree or the sine of 89 degrees. Because it relies entirely on a fixed 10-step sequence of practically free bit shifts, it stays ice cold and ultra fast. It does the exact same amount of cheap work every single time, locking in at exactly 50 penalty points across the entire board. And this gives us our ultimate insight. For an engineer designing a microchip, the worst thing in the world is unpredictability. If a calculation takes 1 millisecond for a small number, but 10 milliseconds for a big number, your system lags. Taylor is unpredictable. But CORDIC is an absolute rock. It guarantees flawless precision in the exact same amount of time, with the exact same tiny 50-point battery drain, no matter what number you punch into the keypad. It is the ultimate hardware hack. Look at what we have accomplished today. We unmasked the illusion of high school trigonometry, went deep inside the microchip of a pocket calculator, and exposed the brutal efficiency of the CORDIC algorithm over the textbook chaos of the Taylor series. We saw how a machine built of sand and wire dodges heavy multipliers and divisions, trading them for lightning-fast bit shifts, and a pre-shrunk magic seed that beats the laws of physics. But our journey into the hardware hacking underworld isn't finished yet. Think about it. Throughout this entire deep dive, our loop returned the final y-coordinate, giving us our sine. But what about cosine? If CORDIC tracks both x and y coordinates through the exact same rotation, where does cosine hide at the end of the loop? That is your challenge for the next episode. Look back at the code and figure out how to extract the cosine instead of the sine without adding a single extra operation. If your mind was blown today, hit subscribe, ring the bell, and let's decode more hidden math together.